Ionization energy is the amount of energy required to remove an electron from an atom or an ion. And you'll see this referred to as first ionization energy, second ionization energy, third ionization energy, and that's just talking about removing electrons from the same atom. So the first ionization energy is going to be the outermost electron. The second ionization energy would be the next one in. The third ionization energy would be the next one in, and so forth. Now, what you'll notice when you see values of these is that they increase the farther in that you go. And so this is kind of a consequence, if you remember from physics, that Coulombs law is, and then you have a constant, let's say, okay, where, or R, or D squared. But anyway, Coulombs law talks about how the force, and in this case we're talking about the force of attraction between the positively charged nucleus and that outermost negative electron. And so that force of attraction, which definitely correlates to the ionization energy, the higher that force of attraction is, then the higher the ionization energy, the more energy it's going to take to pull that electron away from the atom. And so we can see from the expression of Coulomb's law that it's going to be directly proportional to the charge, but it's going to be inversely proportional to the distance that the electron is from the nucleus. And so we can kind of think about it again as we did with atomic radius, that those core electrons, the shielding electrons, they're going to affect or kind of negate some of the charge, the pull from the nucleus. But then also the more energy levels that we have in the atom, then the farther away that outer electron is going to be from the nucleus. So as we look at pulling successive electrons from an atom, right, we're going further in, and so we're definitely removing some of those shielding electrons the further in we go. But then also, as we go to a different sublevel or a different energy level, our outer electron that we're trying to remove is going to be actually closer to the nucleus. So that's why the ionization energy is going to increase as we move closer in, as we remove those outer electrons. One of the things that you'll notice if you look at these values, and say we'll just look at, say, magnesium here. So in magnesium, it looks like pulling that second electron away takes about twice as much energy as it did to pull that first electron away. But then you see how we have a huge jump. It multiplies by, oh gosh, 3 to 4 times as much. So the jump in energy that it takes to get the third one out versus the second is a much larger increase than it was between the first and the second. And so what's happening here is that, and we'll look at magnesium, thinking about those outer electrons in magnesium. And so you have two that are in the S sublevel, and so once you've taken away those two, you are now going down into a lower energy level that is going to be closer to the nucleus. So when after we take off those initial two, all right, so we'll do kind of all right, so the outer electrons of magnesium, it's got 2 electrons in that 3s, okay, and then we'll just kind of, and so then after that, we jump down, and we have our 2p electrons, and then 2s, and then the 1s, and then here would be our nucleus. All right, so we're looking at the distance away from the nucleus. Here's our positively charged nucleus, attracting these outer negative electrons. So I1 is the energy, say, to get that electron right there. All right, and so we've taken that one away, and so now we're pulling this one out of an unoccupied orbital, so it goes up a little bit, takes a little more energy to get that one out of there. And then, but once we take these two, the next electron that we're trying to take is going to be down here in the second energy level. And so we are now a lot closer to the nucleus than we were for the first and second electron. So that third electron we're trying to get is going to be closer to the nucleus because it's in a completely different energy level. And so that's why we see that large jump there. Okay, and if you kind of plot out, do like a little diagram here with these other ones, that's what you'll notice, is that essentially once we remove all the valence electrons, that's where you'll see, to try to get the next electron after all the valence electrons are gone, you're going to see a big jump in energy. And that's because once the valence electrons are gone, you are now trying to pull an electron away from an energy level that is closer to the nucleus than those valence electrons were. And so again, Coulombs law, right, it's going to be, if you take it, you're making our distance smaller from between the charged particles. And so when we decrease the distance, that force is going to increase. Okay, so let's look at our general trends here. And again, we're going to be thinking similarly in explaining these trends, again, going back to Coulombs law. If it's farther away from the nucleus, the force is going to be decreased. And so our ionization energy would be lower. If it's closer to the nucleus, distance is smaller, which means the force is going to be higher, ionization energy is higher. Okay, so here that would explain why as we go down a column, then it's going to decrease, because every time, every row that you move down, that represents another whole energy level of electrons. So your outer electron is on a farther, more distant energy level relative to the nucleus. And so that's why our ionization energy, the energy it takes to pull it away, is going to be less, because it's further away from the thing that's trying to hold it in the atom. Okay. Then looking at, as we go across a period, our outer electron is, it may change sublevels, but if it's in that same period, we're adding it to the same energy level. So our distance, the distance from the nucleus and the ability of those inner electrons to shield that outer electron from the nucleus is not as effective moving across the period. However, moving across the period, the other thing that is definitely changing is we're adding a proton every time we move one more block over. And what that does is that's changing the pull. The attractive force is increasing. So we're increasing the attractive force on there, while the electrons that are being added are not, they're not shielding it as well. And so we're getting very little benefit from shielding. We're getting very little distance added to it. And so the attractive force is going to be stronger moving across the row, which is why the ionization energy is going to increase. The further we go across a period, the more energy it's going to take to pull that outer electron away. Now, you will have noticed, if you look like this graph here, that the trend in first ionization energies is not absolute. And to look at why that is, we need to look at the orbital notations for these electrons. And so here we have So looking at here, group 3A to, or 2A to 3A, and so here we see where it's going from, say, beryllium to boron. So we have beryllium, so again, here's my nucleus, and I've got, well, that would be 1s, are going to be here, all right, and then again, let's do it this way, beryllium and boron. And so here, 1s, and then this is my 2s here. Oops, up there. And then there's my 2s. And then here's my, this one right there. That's, all right, there we go. All right, so when we go from beryllium to boron, okay, so when we look at these and we look at the difference in the outer electrons, beryllium's outer electron is in this 2s sublevel, boron's is in the 2p sublevel. And so when we compare those two, again, this one we've got a little bit farther away from the nucleus for that electron than it is for this electron. And so for that reason, we get a little bit of a deviation in that trend. Once we get past boron, as we can see, then it starts going up again. All right, and then, which I think I just wrote over that. Whoops. Okay, so here is the next one. So here we have the next one between groups 5A and 6A. And so in looking at that, let's look at, so that would be, if we're talking about, again, let's just stay in here. So right there, that little change in the trend is between nitrogen and oxygen. Okay, this one here is nitrogen, that one there is oxygen. So let's, again, look at what's going on there. Well, the outer electrons in nitrogen are in, we've got that 2p. This is our 2p's right there for nitrogen and for oxygen. All right, so there's the 2p's. So let's see what is the difference here. If we look at nitrogen versus oxygen's outermost electron, what do we notice? Well, we notice that the outermost electron in oxygen is being pulled from a full orbital. Whereas if I try to remove an outermost electron in nitrogen, it's coming from an unoccupied orbital. And so if you kind of want to think about it from the standpoint of, even though these guys have opposite spins, there is still going to be a little bit of an assist, if you want to think of it that way, from oxygen, in the oxygen's case, because it's a little bit easier to take an electron out of a full orbital than it is to take one out of a single occupied orbital there, okay? So here we've got a little bit of a repulsive assist that makes it a little easier to get oxygen's outermost electron out than it is to take the one from nitrogen. And so that's why you see this little bit dip in the trend at the halfway mark across the p orbitals. And you'll see that again in the third energy level as well. And we see it in the fourth and the fifth energy level, is that when you are at a half-filled p orbital, the trend is not absolute. That it's a little bit easier to take an electron out of a full orbital than it is to remove it from an orbital that only has one electron in it. All right, electronegativity. The difference between this trend, or this property, and the others is that electronegativity applies to atoms when they are bonded. And so this characteristic is when an atom is in a bond, how strongly does it attract electrons towards itself? And the trend for this is going to follow or be very similar to the ionization energy's trend. So it's going to increase up and to the right. And for similar reasons to what you saw with ionization energy. And so you can kind of see here, but again, you're not, you don't see the little dips in the trends that you do in ionization energy. Okay? And you should notice that nonmetals tend to have fairly high electronegativities, especially the halogens. So when they are in a bond, they are going to tend to pull electrons more towards themselves. And this is going to be more significant to you when you're in the unit that deals with bonding. And that's really where we get into in bonds where electrons are shared. Is one side going to be more negative because you have one atom with a higher electronegativity and it's pulling electrons towards itself more than the other atom it's bonded to. But the trend in general is very similar to the trend for ionization.